4.3 is our assignment today, and it deals with graphing square root equations and cubed root equations. So the general square root equation, y equals the square root of x. If we built a table and we put x and y, x was 0, 1, negative 1, well, let's do 1, 2. So plug 0 into that function. The square root of 0 is 0. The square root of 1 is 1. And the square root of 2 doesn't simplify. It's actually 1.414. So we're not going to plug that in. We are going to plug in perfect squares like 4 and 9. But what happens if I plug in negative 1? I get I. How do you graph I in the coordinate plane? You can't. So negative 1 does not belong to this function, just like every other negative number. If you plug it in, you do not get a real number, which means there's nowhere to graph it, which means there is no graph at negative 1. If we graph those points, the square root function will look like this. Starts at 0, and then it shoots off to the right, going up, and then it levels out. And the further out you go, the more level it becomes. Okay? The cubed root graph, if we built that table, would be x and y 0, 0, 1, 1. And then I don't want to plug in 4. What's a good number to plug in? 8. If I plugged in 8, the cubed root of 8 is 2. What would be another good number to plug in? 27. And I get 3. And that's going to have sort of the same shape as the square root graph. It's just going to be flatter. So if I graph that, if this is the square root graph, then the cubed root graph is going to be flatter. Okay, but what about negative 1? What happens when I plug negative 1 into the cubed root? I get negative 1, because negative 1 times negative 1 is 1, times negative 1 is negative 1. I could also plug in negative 8 and get 2, and I could plug in negative 27 and get 3. So this graph actually has a mirror image on the other side. And that graph exists everywhere. Okay? Well, what if we start moving those graphs around? What if I had the square root of x plus 2 minus 3? Well, we've worked with transforming functions quite a bit. Anything on the inside affects the x-axis, and it works backwards. Anything outside the square root affects the y-axis, and it works normally. So this square root graph would be where? Where would it be? Where would it start? This is going to move it, good, to the left 2, and this is going to move it down 3. And then it's going to look something like that. Okay? Oh, good question. So can I plug negative numbers in? Some of them. I can plug in negative 1. Why? Because when I stick that in, the x is negative, but the plus 2 makes it positive, so I take the square root of a positive. So that's a really good question. Can you plug negative numbers in? Some of them, yes. Only because once you stick them in, whatever else is underneath that square root is going to make it positive. But can I plug in negative 3? No, why not? That 2 is not big enough to negate that, to get rid of the negative with the negative 3. Yes, I could do negative 2, because you can take the square root of 0. Okay. What about y equals negative square root of x minus 1 plus 3? What is that going to look like? So we're going to go right 1 and up 3. What does this do? Flips it upside down. So it'll look like that. Okay. Now, what is the domain of these two graphs? So the domain, what does domain mean again? All x's. So how would you describe all x's in this case? Greater than, equal to? Greater than or equal to negative 2. Because it's everything from here over. Okay? And we need to list that in interval notation. Have you guys done interval notation before? I don't remember. So you could say x is greater than or equal to negative 2. Or you can say something like this. You done that before? Okay. So what you do is you list low, comma, high. What is the smallest x that counts? Negative 2. So we're going to say the domain is x equals negative 2. What is the largest x? Infinity. And then equal to is represented by a bracket. Not equal to is represented by a parenthesis. So is 2 equal to or not equal to? Equal to, so it gets a bracket. And then infinity, can you ever reach infinity? No. So infinity always gets a parenthesis. So that is not a point. So if I said x comma y is 6, 2, that means right 6 and up 2. Okay? But for interval notation, they're both x's. The left side is negative 2 with a bracket, which means equal to. And the right side is infinity with the parenthesis, which means not equal to. Okay? How would you describe this domain? So we would do great. So the left side is 1 and the right side is infinity. Okay? What if I had this graph? What would the domain be? So the domain, x is equal to, what's the farthest most left number? Negative infinity. And what is the rightmost number? 3. Infinity gets parenthesis. 3 gets a bracket. Okay? What if I had this graph? What would the domain of that graph be? What is the furthest most left number? Negative 1. And the furthest most right number? 2. Is negative 1 equal to? Yes, so it gets bracket. And is 2 equal to? No, so it gets a parenthesis. So that's interval notation. Okay? Equal to gets bracket, not equal to gets parenthesis, and you always do leftmost and rightmost. All right, let's take a look at our ALEKS assignment. Oh, one thing I forgot, sorry. If I had this graph and next to the third graph, what's the domain there? All real numbers. How do you represent all real numbers using interval notation? Well, what is the furthest number to the left? Negative infinity. What is the furthest number to the right? Infinity. And infinity always gets a parenthesis. Oh, probably don't want to do that one. Okay. So all you're doing there is plugging in those values. So plug in -9. The square root of -9 is I. So that one does not have a real number. 0 would be 2. 4 is going to be the square root of 4, which is 2, plus 2 is 4. And 36 is going to be 6 plus 2, which is 8. Okay. All right. So what is the domain here? Well, one way to find the domain is to graph it. Where is this graph? What happens when I add 8 on the inside? It's going to move it left 8, so it's going to look like that. So the domain is going to be -8 to infinity. Wow, that was a really good 8. Like that. Oh, well, that really surprises me. Okay, so you would do x is greater than or equal to -8. All right, well, there's another way to find it. What do I know about those possible numbers? If I take a square root of a function, what can you guarantee about the numbers inside the square root? What do they have to be? What sort of numbers can you take the square root of? Positive. Can you take the square root of a negative? Not using real numbers. What about 0? Can you take the square root of 0? Yes, it's 0. So if this is, say, the number b, then I know that b is greater than or equal to 0. So whenever you have a square root function and it asks you what the domain is, all you have to do is set this up and solve. So here's what I mean. If I have the square root of 8 plus x, then I know that 8 plus x is greater than or equal to 0. It has to be that way. We are not allowed to take the square root of negative numbers on a real graph. So we solve, and we get x is greater than or equal to -8. Okay? What if I had the square root of 2x minus 6? Well, 2x minus 6 has to be greater than or equal to 0. So we add 6. 2x is greater than or equal to 6. Divide by 2. X must be greater than or equal to 3. And notice, as long as I obey this constraint, I will not take the square root of a negative number. So if I plug in, say, 4, 2 times 4 is 8, and 8 minus 6 is 2, and I can take the square root of 2. But watch what happens when I try to plug a number that's not in that range, in that domain. Let's say I tried 1. Will 1 work? No, it's not big enough to overcome the -6. So 2 times 1 is 2, and 2 minus 6 is negative, and I can't take the square root of a negative. So whenever you're asked to find the domain of a square root graph, just take the inside and then write greater than or equal to 0. There is one little trick that happens every once in a while. Hopefully you haven't forgot it. What if I had the square root of 9x minus, 9 minus 3x? So 9 minus 3x is greater than or equal to 0. Subtract 9, and I get -3x is greater than or equal to -9. Now what? Divide by -3, and I get, good. X is less than or equal to 3. Why did I flip the inequality? I divided by a negative. Okay. Why do you flip the inequality when you divide by a negative? Does anybody have any idea why? Yes, you were told to. I will teach you why that's the case. So let's consider x plus 1 equals 5. So every equality is a balance. The left side weighs exactly the same amount as the right side. So on the left side, I have this block called x, and then I have 1 pound. And then on the right side, I have 5 1-pounders. And it's perfectly balanced. If I want to figure out how much x weighs, then I can subtract 1 pound from the left side, which would make the balance lean to the right. So what do I do to maintain the balance? I get rid of one of them on the right side. I can do anything I want to the left side as long as I do exactly the same thing to the right side. Does everybody understand that? Okay. And this shows you that x is 4. Okay. What if I had 2x equals 4? What does that look like? Well, I have 2 x boxes, and then I have 4 pounds. Well, let's get rid of half of everything. I get rid of half of the x's, and I get rid of half of the 1-pounders, and I get x equals 2. Okay? All right. How do we represent this? Well, I have an x, and I have 3 pounds. What about the -7? That number's larger than I need it to be. Let's change it to a 2. How do you represent -2? Well, it's not pulling down like all of the other weights. It's pulling up. So what I have is a balloon that has 1 pound of force in the vertical going up. Does that make sense? So now it's balanced. X has an unknown weight. There are 3 pounds on the right side, but on the left side I have 2 balloons that are pulling up, and they are pulling up with the force of 1 pound. Okay? So what happens when I cut the string on those 2 balloons? Which side weighs more now? The right side or the left side? If you cut the balloon strings, so the balloon strings are pulling up on the left, if I cut them, which side is heavy? The left side is now heavy. So how do I offset that? How do I fix it? I add extra weight to the right side. How much extra weight? 2 pounds. And now it's balanced, and we find out that x weighs 5. Okay, now this is a really long explanation to why you have to multiply. When you multiply by a negative, you flip the inequality. Okay, let's consider this. What does that mean? Well, it's not balanced. Okay? So if we set up our fulcrum, we know that our x box is heavy. It's heavier than any amount smaller than 4. Right? So if I put 1 pound there, is it going to balance? No. If I put 2 pounds there, is it going to balance? No. If I put 3 pounds, is it going to balance? No. If I put 4 pounds, is it going to balance? No. But if I put anything bigger than 4, then the right side will weigh more. All right? I skipped one step. Let's say I had x plus, nope, let's say x minus 1 equals 2. Okay. So I have a weight of x, I have a balloon with 1 pound, and then I have 2 1-pound weights on the other side. Okay? What happens when I times this by -1 and I get negative x plus 1 equals -2? How would you draw that? X becomes a balloon. The balloon becomes a weight, and the 2 1-pounders become balloons. Is it still balanced? Yes. So if this is balanced, and I flip every balloon into a weight and every weight into a balloon, it's going to look like that, and it still is balanced. Where before the weight was pushing down, now the weight is pulling up, but it's the same force, so they're equal. Okay. So, what happens when I times this by -1? Okay, and let's just put, well, no, 4 will work. Okay, so now my x becomes a balloon, and my weights become a balloon, but that picture is wrong. Why is that picture wrong? Why? Good job. This is the heavier weight, right? X weighs more than 4 1-pound rocks, right? So if I turn X into a balloon, which is stronger, this balloon or those 4 balloons? The X balloon is stronger. It weighed more before, and now when we negate it, it's going to float better. So the graph would actually look like this. Wow, that was a long explanation. So why do we have to flip the inequality when we multiply by -1? Because when you turn a heavy weight into a strong balloon, then your balance goes from wherever it is to the opposite. That's why you have to multiply, you have to flip the inequality whenever you multiply by -1. That was a really long explanation. Does that make sense? Eliza's just saying, I was fine when I just was told to do it. Okay, let's look at some more of these. So we have the function t equals 2.01 times the square root of L. If a pendulum is 12.96 meters long, how long does it take to swing back and forth? You're just going to plug this in there. 2.01 times the square root of 12.96. Whatever number that is your answer. Okay. What is the domain of this? Well, all we have to do is set the inside greater than or equal to 0. We subtract 54. Negative 9x is greater than or equal to negative 54. Divided by negative 9. And I get x is less than or equal to 6. So what numbers are you allowed to plug in? Anything from 6 down. Anything above 6 will create a negative number. Right, evaluating a cubed root function. You're just going to plug in 8, take the cubed root, add 1. I'm going to plug in negative 64, take the cube root, add 1. Okay, graphing a square root. So where is this graph? Starts at negative 4. Okay, we have to plot 4 points. So the first point is easy. Over 1, up 1. And then, should I go over 2? No. Should I go over 3? Now, the square root of 3 is not a nice number. But if I go over 4, that would be up 2. And then, what would the next one be? Over 5, 6, 7, 8, 9, up 3. And you need 4 points to graph it. So over 1, up 1, over 2, up 4, over 4, up 2, over 9, up 3. Okay. Okay. What is the domain of f? Well, cubed roots have both a right side and a left side, so the domain is all real numbers. So it'd be from infinity, negative infinity to infinity. But if the root is even, then we just have to take x minus 5 and write greater or equal to 0, add 5, and I get x is greater than or equal to 5. How would I represent that using interval notation? We would use this one, bracket 5 to infinity, like that. So if the root is 3, 5, 7, 9, or any other odd number, then the domain is all real numbers. But if the root is a 2, a 4, a 6, or any other even number, then you have to set the inside greater than or equal to 0. Okay, where is this graph? Negative 1, 5. So it starts here, and then over 1, up 1, over 4, up 2, and over 9, up 3. Like that. Okay. Now we're going to graph a cube root function. Where is the cubed root of x plus 4? So it's over 0, up 4. So we're going to start right here. And plot 2 points to the left and 2 points to the right. Okay? So over 1, up 1. And then over, what would the next one be? Over 8. 2, 3, 4, 5, 6, 7, 8. Up 2. And then on the other side, over 1, down 1. Over 8, down 2. Right there. So this would be the graph. All right. Get to work.